Hello and welcome to the sixth and final video of the FP3 chapter, Matrices. Start a question on the screen for you. Pause the video now if you've got time and give this a go. I will go through it even though the video is quite long because this is directly related to what we need to do in this video. Show that -2 is the only real eigenvalue of A. So if you remember from our previous work, to find the eigenvalues we need to solve the equation determinant of A minus lambda I is equal to 0, this thing called the characteristic equation. A minus lambda I will always have a very similar sort of look to it. We'll have minus lambda along the leading diagonal, and all of the remaining elements will be unchanged. And then we need to find the determinant of that and set that equal to 0. So 2 minus lambda times the minor, which is 3 minus lambda times minus lambda minus 5 times 1. Then minus the second element, so it's minus 1 times its minor, 0 minus 10 plus the third element times its minor, 0 minus 2 times 3 minus lambda. And that has to equal 0 when we're solving for lambda. So we get 2 minus lambda times lambda squared minus 3 lambda minus 5 minus 10 minus 6 plus 2 lambda. So I can expand this out, collect like terms. We end up with minus lambda cubed plus 3 lambda squared plus 2 lambda squared plus 5 lambda minus 6 lambda minus 10, and then from outside the bracket minus 10 minus 6 plus 2 lambda. Okay, collecting all of this, we've got minus lambda cubed plus 5 lambda squared, and then all together with the 2 lambda at the end as well, we have plus lambda and then minus 26. And this is an example of a situation where something in the question is helping you to solve your cubic, because they're telling us show that -2 is the only real eigenvalue. So we know that -2 is an eigenvalue. So we know that one of the brackets here is lambda plus 2. And the question is, can we find the quadratic equation to go here and then show that that has no real solutions? So in here we've got minus lambda squared, that will have to be a minus 13, and if you work it through you find that there is a 7 lambda here, and I know that so quickly because I did it before I started the video. So you get lambda is equal to -2, and then this here has no real solutions if you put that either on your calculator or into the quadratic equation. So we have shown that -2 is the only real eigenvalue of A. In this final video of the FP3 module, we are going to reduce symmetric matrices to diagonal form. And to do this, we're pulling heavily on the previous video with eigenvalues and eigenvectors. Take note though, we're working with symmetric matrices in this video. So each of the questions in the examples you'll notice is a symmetric matrix. Here we go, a few notes to start us off. We already know that a symmetric matrix is one that is equal to its own transpose. We also now need to know that a diagonal matrix is defined as one in which all the elements that are not on the leading diagonal are 0. like this. So it doesn't matter what these three elements are. What matters is that all the other elements are zeros. And this is called the leading diagonal, as opposed to this diagonal here. So we're always going to be talking about the leading diagonal. And this is a diagonal matrix. The most obvious example that you already know is the identity matrix, where A, B, and C are all equal to 1. We also need to know this thing called an orthogonal matrix. Now, an orthogonal matrix is one in which the matrix times by its own transpose gives you the identity matrix. And you know that a matrix times its own inverse always gives you the identity matrix. So that's the same as this statement, that an orthogonal matrix is one where its transpose is the same as its inverse. So if this is true, then this is true. If this is true, then this is true. And if either of these are true, then it is an orthogonal matrix. What's important about this is that an orthogonal matrix is made up of column vectors. If you were to take each of the columns and split them into separate vectors, those vectors are all perpendicular to one another. And orthogonal is another word for perpendicular. So here's the general statement. If a matrix is made up of these 9 elements, and the transpose is equal to the inverse, i.e. it is an orthogonal matrix, then the columns, if you split off the first column, give it its own vector. The second column, you make that into a separate vector, and the third column into a separate vector. Then these two vectors are orthogonal, so a dot b is equal to 0. So are these two, and so are these two. All the different pairs, if you do the dot product, give you 0. They are all perpendicular to one another. And that's the idea of an orthogonal matrix. We're going to use this idea to help us find the diagonal matrices. Okay, the next step is to take note of how these things relate. So we can reduce, or you might see the word diagonalize, a symmetric matrix into a diagonal matrix using an orthogonal matrix P. And these are connected with an equation such that if P and its transpose and the diagonal matrix D and the original matrix you're working with A, if they all satisfy this equation, then this is the diagonal matrix for this symmetric matrix. And obviously we're going to need to know P in order to put it into this equation to find D. And that will be part of our process. To remember this equation, I use a very silly little image in my mind, because if you read this as P tap equals D, then here's a tap and it's producing P's. So P tap equals D. So if you hear me say P tap, what I mean is P transpose times A times P. And of course, because of what we just said about orthogonal matrices, we don't have to have the transpose here. We could have the inverse, because for an orthogonal matrix P, these two are the same. So you could instead use this. Although generally it's easier to find the transpose than it is the inverse. And to do this, we need to find this P, and P will be made up of the normalized eigenvectors of matrix A. So D will be related to A, it will be the diagonal of this symmetric matrix, but P is also related to A. It is made up of the eigenvectors of A normalized. So that's what we're going to need to do. We'll start with A. We'll have to find the eigenvectors of A, normalize them, create the matrix P, put it into this equation or this equation, do the multiplication, and find the diagonal matrix D. And that is written here step by step. Find the normalized eigenvectors of A, create P using those eigenvectors as the columns of P, and it won't matter which order they go in. We'll come back to that at the end of the video. Then step 3, find the transpose, substitute these into the equation, and find D. And you'll notice I put this one in brackets, because actually there's a slightly easier, quicker way to do that last step, to find D once you've found P, but we'll come back to that at the end. We're going to go through this process in order to realize what that quicker way is. So into our examples. Reduce the matrix A to a diagonal matrix, and I've started off with a 2 by 2 matrix here just because it's quicker and easier, and then we'll go into a 3 by 3. So first I need to find the normalized eigenvectors of A, which means I need to find the eigenvalues. To find the eigenvalues, we're doing the determinant of A minus lambda I equals 0. It's a little bit easier with 2 by 2 matrices because the determinant is easier to find. 2 minus lambda, minus 1, 2 minus lambda. And just a reminder here that we're working with symmetric matrices. So the determinant of this is equal to 2 minus lambda, minus 1 times minus 1 is 1. So we've got lambda squared minus 4 lambda plus 4 minus 1. So that's lambda squared minus 4 lambda plus 3, which we can factorize. Minus 3 minus 1, which gives us our 2 eigenvalues. Okay, for the eigenvalues, we then need to find our eigenvectors. So if we've got lambda is equal to 3, then we are doing AR equals lambda R to find R. So we've got 2 minus 1, 2 times xy is equal to 3 xy. So we've got 2x minus y is equal to 3x, which gives us the relationship x must equal minus y. And then we've got minus x plus 2y is equal to 3y, which gives us y equals minus x, the same relation. So the eigenvalue 3 gives us the eigenvector. Let's choose, nice and easy, 1, minus 1. But you must remember to normalize these eigenvectors. The magnitude of this vector is not 1. We've got 1 squared plus 1 squared, that's 2. The magnitude of this is the square root of 2. So to get the normalized eigenvector, I have to divide this by its own magnitude. So the normalized eigenvector is 1 divided by the square root of 2, and minus 1 divided by the square root of 2. And that is the normalized eigenvector I'm going to use to create P. Okay, I'm running out of space a little bit. I'll jump over to the left for lambda is equal to 1. And here we get 2x minus y must equal to 1x, and minus x plus 2y is equal to 1y. So I've got minus y is equal to minus x, so that's y is equal to x, and here I've got the same thing. So a very similar relationship, so I'm going to choose the easiest 1, 1. And again, that's not normalized. That does not have a magnitude of 1, so the normalized eigenvector here is going to be 1 over root 2, 1 over root 2. So my P I create by using these two column vectors as the columns of P. And I can put this one first, and then this one, or I can do it the other way around. At this point it doesn't matter. We'll come back to what the consequence is if I choose one way or the other later in the video. So I'm going to choose, I did the yellow one first, so let's put the yellow one in first. 1 over root 2 and minus 1 over root 2 is the first column of P. And then 1 over root 2 and 1 over root 2 is the second column from the blue one. And that is my orthogonal matrix P. What I need to do now is use that, find the transpose, put it into this equation, do the multiplication and find D. So I've got P is equal to 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2. So my equation, p tap equals d, is going to be the transpose of this, 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2, times a times p is equal to d. And of course, you must remember the order for matrix multiplication is very important. The transpose of t must be on the left, p must be on the right, and a must be in the middle. However, once you've put them in that order, it doesn't matter if you multiply these two first or if you multiply these two first. But just having them in the correct order is very important. So I'm going to do the leftmost two first. So we get 2 over root 2 plus 1 over root 2. So here we have 3 over root 2. Then we have a minus 1 over root 2, minus 2 over root 2 is minus 3 over root 2. 2 over root 2 minus 1 over root 2 is 1 over root 2. And minus 1 over root 2 plus 2 over root 2 is also 1 over root 2. And then we have to multiply that by this one. And yes, you will often have surds floating around. I wouldn't recommend rationalizing these until the end if you need to rationalize them in the diagonal matrix, which usually you won't. So just leave them where they are. Usually the roots will disappear, as they will here, as we multiply this. We get 3 over 2 plus 3 over 2, so that's 6 over 2. 6 over 2 is 3. Then we get 3 over 2 minus 3 over 2, which is 0, which is good because the non-leading diagonal elements in the diagonal matrix at the end should always be a 0. So if this one or this one are not zeros, I've done something wrong. 1 over root 2 times 1 over root 2 is 1 over 2, minus 1 over 2, that's a 0, good. And the last one, 1 over 2 plus 1 over 2 is 2 over 2, 2 over 2 is 1. So here is my diagonal matrix associated with A, and here is my orthogonal matrix associated with A, and I can tell you that for sure because they satisfy this equation. Okay, it's a long process. I won't talk as much through this one, I'll just try and get it done. We're going to do the same thing now with this 3×3 matrix. First, normalized eigenvectors. Determinant and then we get a 0 for the next element, so here's my determinant. What I'm going to do here, instead of expanding everything out, I'm going to factorize the minus 2 minus lambda. Two minus lambda minus 1. So I can simplify the bracket here by expanding and collecting again. which gives us the 3 eigenvalues. -2, 3, and 1. Okay, from here we need the eigenvectors, and then to normalize them. So we've got -2, 3, and 1. And this one is all invariant points, so the vector will become exactly the same. And that tells me that z is equal to -x. That tells me y must equal 0. And that tells me the same as that told me. So long as z is equal to -x and y is 0, I can choose any number, so let's choose 1 for x, and z will be -1. So the normalized eigenvector from this eigenvalue will be 1 over root 2, 0, -1 over root 2. Then we have lambda is equal to a -2, so we get 2x plus z equals -2x, which tells me z must equal -4x. -2y must equal -2y, which tells me nothing at all about y, because they will just cancel. And then x plus 2z equals -2z tells me x must equal -4z. Now for these two to be true at the same time, x and z must both be 0, and y can be anything, except I can't have a 0 vector, so it can't be a 0 in y, but anything else is okay. So 0 for x and z, and a 1 for y. And that's particularly nice because that is already normalized. The magnitude of that vector is 1, so I can leave that how it is. Last one. Lambda is equal to 3. 2x plus z must equal 3x. Tells me z must equal x. -2y is equal to 3y. Tells me that y must equal 0. And x plus 2z equals 3z. Tells me the same as this one told me. So similar to the first one, y must be 0 and z and x must be related. In this case they must be the same. And the normalized eigenvector here, 1 over root 2. 1 over root 2. So my p, I'm going to make up with these 3. I will keep the same order again. I'll put this one first, this one in the middle, and this one third. So I get 1 over root 2, 0, 1 over root minus 1 over root 2, 0, 1, 0, 1 over root 2, 0, 1 over root 2. And this is my orthogonal matrix. I'm going to transpose this, put it into the equation p tap equals d, and find d. So we've got p, 1 over root 2, minus 1 over root 2, 1 over root 2, 1 over root 2 like this. In front of that we've got a, and in front of that the transpose of p. So we change the columns into the rows, which puts the minus over there, and 1 over root 2, 0, 1 over root 2. And all of this multiplied gives me d. And again, now I've put them in the correct place, I can do whichever pair first I want. I'm going to do this pair first. Two over root 2, 0 minus 1 over root 2. That's 1 over root 2. Continuing on, we get 0, 0, 0. That's nice. 1 over root 2, 0 minus 2 over root 2. 0, 0, 0. 0 minus 2, 0. 0, 0, 0. 2 over root 2, 0, 1 over root 2, that's 3 over root 2. 0, 0, 0, 1, 0, so that's always nice. 1 over root 2, 0, 2 over root 2, so that also is 3 over root 2. A final multiplication gives me 1 over 2, 0 plus 1 over 2, that's 2 over 2, which is a 1. I get 0, 0, 0. 1 over 2, 0 minus 1 over 2, so that's 0, that's good. Remember, this is a diagonal matrix. 0, 0, 0. Then we get 0 minus 2, 0. 0, 0, 0. 3 over 2, 0 minus 3 over 2. 0, 0, 0. And finally, 3 over 2, 0, 3 over 2, 6 over 2, 6 over 2 is 3. And I wonder if you have noticed something. These numbers, 1, minus 2, and 3, are the 3 eigenvalues. And if I go back a little further, the 2 numbers we had in the diagonal matrix, 3 and 1 for the 2 by 2 matrix, were also the 2 eigenvalues. So this is where we're going to have a slightly easier final step. Rather than doing this and putting it all into the equation, basically this whole screen here, you don't need to do this step, because once you've got P here from the normalized eigenvectors, you can then find D directly from your eigenvalues, and this is where the order becomes important. Whichever column vector you put first, here the blue one, that's the eigenvalue that needs to go in the first column. And in the first column of my diagonal matrix, I must have zeros here and here, so the eigenvalue 1 goes here. Then I had this one second, so the minus 2 needs to go in the second column, and again I must have zeros here and here in a diagonal matrix, so the minus 2 must go in the middle. And then I put column 3 third, so 3 has to go in the third column with zeros here and here, so 3 must go in the bottom here. And we get 1, minus 2, 3, which is the same 1, minus 2, 3 here. So you can skip out this final step and replace it with this slightly easier and certainly quicker create D by using the eigenvalues in the same column order as the eigenvectors in P. And you'll notice that that does give you some flexibility. If we had chosen instead to put the green column first and the blue column second, we would have a slightly different P matrix. But that's okay. All that would mean is the minus 2 would go here and the 1 would go here, and it would still satisfy this equation. So you would have, for a 3 by 3 matrix like this, you would have 6 different possible pairings of P and D, depending on what order you put your column vectors, and that would relate to the order of your eigenvalues in D. So if we need step 3 in the final example, I won't do the matrix multiplication like this, I will use this idea instead. But before we get to the last example, one final thing to note is that there's an alternative way to think of all of this, and that is this fancy word, Eigen decomposition. And if you rearrange this equation using the inverse p, you can get this equation. And rather than creating an equation that equals d, this focuses on the idea that a is equal to this. And the sort of thing to think here is that the transformation that matrix A represents can be thought of as a three-step process, applying some probably rotational transformation, an enlargement, and then reversing the inverse of that rotation. And what that's doing, if you want to think of the three orthogonal axes x, y, z in three-dimensional space, you could think of this as rotating your axes to align with the three eigenvectors of the matrix A, that is, the three directions that are not going to change, then doing a scaling, an enlargement along those three directions according to their eigenvalues, and then rotating the system back. And that's basically a way of breaking down what the matrix A is doing as its transformation. Don't let that worry you though, that's just a little side note. It's unlikely to come up in your exam in this form. So here we go, the final example of the final video. The matrix A is this. And notice again it is symmetric. Part A. Verify that 2, 1, 1 is an eigenvector of A and find the corresponding eigenvalue. Verify, not show. So all I need to do is put this in and show that it works. Part B. Show that -6 is another eigenvalue. Find the eigenvector. Part C. Given the third eigenvector as this, find a matrix P and a diagonal matrix D that satisfies this equation. Okay, I'll take it step by step so that I've got enough room on the screen. Part A. Verify this is an eigenvector. So if we do 7, 5, 5, 5 minus 2, 4, 5, 4 minus 2, and apply that matrix onto this vector, assuming it is an eigenvector, this will come up unchanged, except perhaps scaled. So maybe a 4, 2, 2, or a 20, 10, 10, something like that. And if that's true, we verified it is an eigenvector. So what we get, 14 plus 5 plus 5 is 24. So I assume the next two numbers should be a 12 and a 12, but let's just check. 10 minus 2 is 8, plus 4 is 12 indeed. 10 plus 4 minus 2 is also 12. Yes. So that is 12 times 2, 1, 1, which simultaneously verifies that it is an eigenvector and tells me the eigenvalue. So one of my eigenvalues is 12. Show that -6 is another eigenvalue of A, find the corresponding eigenvector. Okay, well we know finding the eigenvalues means solving the determinant of this matrix. But in order to show this, I don't need to go through the whole process and find all of the lambdas. What I could do is just put -6 into lambda here, and then show that the determinant of that is 0. So that's what I'm going to do. So we get 13, 5, 5, 5, 4, 4, 5, 4, and another 4. The determinant of this is 13 times 16 minus 16, that's a good start, minus 5 times 20 minus 20, plus 5 times 20 minus 20 again. And of course all of those are 0. So -6 is indeed an eigenvalue of A. Okay, find the corresponding eigenvector. So we have 7, 5, 5, 5 minus 2, 4, 5, 4 minus 2 applied to x, y, z. must give us minus 6 times x, y, z. Split into green here, so we're going to have 7x plus 5y plus 5z must equal minus 6 times x. 5x minus 2y plus 4z must equal minus 6 times y. And 5x plus 4y minus 2z is equal to a minus 6z. Now this looks like a much more complex set of equations to solve, but a little bit of inspection shows you that if z and y are nicely paralleled here and x is the same, then there probably are a few 1's floating around. So if I make y a 1 and z a minus 1, then this statement is true if x is 0, and then make y a 1 and z a minus 1, then this statement is also true. So if I make y equals 1 and z equals minus 1, and then just check this last one here, minus 1 plus 1 cancels out, 7x equals minus 6x, yes, x will have to be 0, then that works. So 0, 1, minus 1 is an eigenvector. It's not yet a normalized eigenvector, but at this point they haven't asked us for that. So this is the eigenvector that corresponds to minus 6. Part C. Given that the third eigenvector is this, find a matrix P and a diagonal matrix D such that this equation is true. So first I'm going to find the eigenvalue of this eigenvector, and then we can just write down D and P quite easily. So if I save space by sticking it here, that gives me 7 minus 5 minus 5 is minus 3. And already I should be able to write down the rest, but I'm going to go through it just to make sure it's correct. 5 plus 2 is 7, minus 4 is 3. 5 minus 4 plus 2 is also 3. So minus 3 times the original vector, which gives me my third eigenvalue of minus 3. From here, in pink, the final answer, D. I'm going to put this one first because it's on the screen. Minus 3, 0, 0. And P is the normalized eigenvectors. Don't forget to normalize them now. So 1 squared plus 1 squared plus 1 squared gives me a root 3 as the magnitude. So 1 over root 3 minus 1 over root 3 minus 1 over root 3. Then I've got 0, 1 minus 1 with the eigenvalue minus 6. Let's put minus 6 in the next column, and it's 0, 1 over root 2 minus 1 over root 2. And then the third one, back on the first screen here, the eigenvalue was 12 and the eigenvector was 2, 1, 1. So we've got 2 squared, 4, 5, 6. Square root of 6 is what we need to divide this by to get the normalized eigenvector. So we've got a 12 to finish off our D matrix, and 2 over root 6, 1 over root 6, 1 over root 6 finishes off our orthogonal matrix P. And if you had time and you wanted to double check, you could of course put these into here and make sure that it was true, that everything was okay. But this process will give you the correct answer if you followed it through correctly. Orthogonal matrix P, diagonal matrix D without the multiplication. And that is the end of these videos for FP3. You can now practice using questions from exercise 6G for this specific video's process. You can then practice chapter 6, all of matrices, from the review exercise at the end of the chapter. Review exercise 2 covers the second half of the book. Then of course there's a practice paper at the end. Basically all the questions in the book at this point are fair game. Good luck with your exam, and I won't see you in another video because this is the highest level video that I do. Good luck at university.